This video is going to be introducing the preliminary concepts of Chapter 3, mainly focusing on the ideas of light and energy, the wave-like properties of light in particular. So we need to start by looking at something called the electromagnetic spectrum. Now, the electromagnetic spectrum covers all frequencies of all radiation that exists in our universe, going from the very, very, very high energy gamma rays to the very, very low energy radio waves. Now, any form of radiant energy in the spectrum is considered electromagnetic radiation. We tend to focus most on this little band in the spectrum called the visible light spectrum, and it covers light that is in about 400 nanometers to 750 nanometers in wavelength. And you can see that even in this spectrum, we have some areas that we have a hard time seeing. So right around here, around 410 or so, that purple light becomes a lot less visible to us, starts to cross over into the ultraviolet region, which we cannot actually see. Right here around 725, same thing. Our red kind of fades to black as we have no way of being able to see that infrared light that is there at those wavelengths. Now, all wavelengths, all electromagnetic radiation can be described in two different ways, using something called wavelength being the distance between a wave's peaks or between its troughs, like so. Frequency, on the other hand, can be determined and looked at by looking at the relationship between the speed of light and the wavelength of light. So since all electromagnetic radiation travels at the same speed, the speed of light, 2.998 times 10 to the 8th meters per second, since it all travels at that speed, the shorter the wavelength is, the more waves we're going to see over that period of time. So our frequency is going to increase as our wavelength decreases. There is an inverse relationship between the two. And that is reflected in this equation that the speed of light, again, 2.998 times 10 to the 8th meters per second, is equal to the wavelength of light and that wavelength is given to us in meters, and the frequency of light, which is given to us in reciprocal seconds, sometimes referred to as hertz. And so the relationships between those two variables are as follows in this equation. And we can rearrange this equation to figure out the frequency of any light based upon the speed of light, which is a constant, and the wavelength of light that exists in meters. So with that in mind, we can do some practice questions like these to help us to figure out the relationship and the quantities associated with light. And for that, we are going to need another equation for this one on the bottom, which we'll get to in just a minute. The frequency of light associated with a wavelength of 640 nanometers. So using the speed of light equation, wavelength times frequency equals the speed of light, I can calculate the frequency, relatively easily. Just rearrange it. Frequency is equal to the speed of light over wavelength. And now I need the speed of light, 2.998 times 10 to the 8th meters per second. And the wavelength of light was 640 nanometers. Now, before we go punching this into our calculator, we need to recognize that we have a unit mismatch in our distances. Speed of light is in meters per second. The wavelength of light is in nanometers. This is where our knowledge of the metric system is going to come in handy. We should know that there are 1 billion nanometers in 1 meter. So if we take this number and divide it by 1 billion, we would get the number in meters. And so we could do that. And if we did that, we would get 6.40 times 10 to the negative 7th meters as a result. We can also cheat this slightly using our scientific notation know-how. If we flip this around and say that 1 nanometer is equal to 10 to the negative 9th meters, then we can substitute 640 times 10 to the negative 9th as our meters and be okay. Now, granted, we know that this is not proper scientific notation, but we're plugging this into our calculator, and our calculator actually doesn't care if it's proper scientific notation or not. It's going to automatically convert it to whatever is the correct form anyway. So if I do this calculation, I'm going to get 2.998 times 10 to the 8th divided by 640 times 10 to the negative 9th. I'm going to get to 3 significant figures, 400 or 4.68 times 10 to the 14th. The unit here, my meters have canceled out. I'm left with just 1/seconds. So we can leave it like that, or we can call it by its other common name, hertz. So that is the frequency of light associated with that particular wavelength. Now, the secondary question here is how much energy is in that wavelength? Well, for that, we're going to need another key common equation, and this is called the energy equation, sometimes referred to as Planck's equation, because it includes something called Planck's constant. Planck's constant is H, and it's in for 6.626 times 10 to the negative 34th joules, which is a unit of energy, the SI unit, the common derived unit of energy used by the metric system, multiplied by seconds. So to get the energy, I'm going to take Planck's constant, 6.626 times 10 to the negative 34th joules times seconds. I'm going to multiply it by my frequency, 4.68 times 10 to the 14th reciprocal seconds. Seconds times reciprocal seconds are going to cancel out. I'm going to be left with just joules. And I'm going to get to 3 significant figures again, 3.10 times 10 to the negative 19th joules. Now, this doesn't seem like a whole lot of energy, and it isn't. But we have to understand that this is the energy of a single light wave, and not a terribly energetic one at that. If we go back and look at where 640 nanometers is on our light scale, we're talking about somewhere here in the yellow-orange range. So not terribly energetic light to begin with. So one of the things that was generated out of this early era of physics and chemistry is they started doing a lot of experimentation. We talked in chapter 2 about some of that experimentation as it pertained to the atom itself. We looked at things like the Thomson cathode ray tube experiment, the Rutherford gold foil experiment, the milk and oil drop experiment, and how all those things played a role in understanding the atomic theory of the day. Well, some similar kinds of things were going on as we were trying to get a handle on understanding light. And one of the things that they were able to do is they took a spectrum of sunlight. And so when we think of white light, we usually think of it as this continuous band of colors, no dark spots in between. But when they did this kind of spectrum for sunlight, they noticed that there were these very thin, very narrow, but dark lines that were breaking up the continuous transition from one color to the next. These were known as Fraunhofer lines, mainly named after the scientists who first discovered them. But I've got, as we started to progress, we noticed that not only are these lines present in samples of sunlight, if we actually excite a sample of a gas like hydrogen and get it to begin to emit light, we'll notice that the bright line spectrum in hydrogen doesn't have a whole bunch of continuous lines either. It's very discrete. There are 4 lines here that we can see very discreetly in that bright line spectrum. And if we take a continuous spectrum of it, where we're looking at the light that is reflected instead of emitted, we see that there are 4 dark lines that show up in that spectrum as well. And what's interesting is that these lines all correlate to each other. So look, we've got a line here just after 400. It's right there in this dark line spectrum. We've got another one here right around 435 or so. It's right there as well. We've got one right here around 480, and it's right there as well. We've got this other one here at 650, and sure enough, it's in this dark line spectrum at 650 as well. So there's something funny going on here. Light on its own, we think of as having these wave-like properties. And those wave-like properties generally give us continuous spectra. But what's interesting is when we start to look at elemental samples, we see that elements are capable of absorbing and emitting light as well, but they don't do it continuously. They do it in a discrete fashion with these very well-formed dark and bright lines. So the question I have, and I want to pose to you, if you're watching this and you've got your top hat open, I want you to go in to the assignment on Top Hat. This is assignment 3-1. I want you to pause this video and think about it a little bit. Why are the bright lines and the dark lines in the same locations? Why are certain wavelengths susceptible to those bright and dark lines? Why isn't an atomic spectrum continuous? So there's no right or wrong answer here. I'm looking just for where's your head at? And so if you can pause the video, go ahead and enter that response in. Don't put it in here. It's not going to register anything. So go in through assignment 3.1 and do that. Don't go through the text reply because again, it's not going to do what you need to. But go ahead and pause the video, enter your response, and then come back. And I'll be waiting for you on the other side. All right, so the answer to the question has to do with something called quantization. Quantization is the phenomenon that tells us that atomic emissions are quantized. So when we look at those spectra, what we are seeing is that there is a very specific energy that is allowed for that light. And the reason we only see those particular lines is because those are the only allowed energy transitions that exist. And so we call these specific lines quanta. They're very specific energies. Now, if you think about it in kind of context to maybe something, other terms that you've heard, the word energy level kind of starts to enter into the conversation with this idea of quantization. If you can think about an atom as having a number of different energy levels, well, if we think about these energy levels as existing, and as we get further and further away from the nucleus, we get higher and higher and higher energies. Well, then it kind of makes sense that if I want to go from here to here, that's going to require a certain amount of energy. And the resulting light that comes off this of that energy transformation is going to have a very specific energy as well. And so if we think about things in terms of energy levels and the fact that quantization restricts what energies those energy levels can have, then it becomes a lot more reasonable to see why we don't have continuous spectra for atoms, because atoms aren't governed by the same kinds of rules. We're not talking about the reason we see light is because of energy transition with regular light, but with atoms, it's exactly what's happening. So the theory in play here is something that is proposed initially by Max Planck. And what Max Planck says is that when objects emit electromagnetic energy, they always do so in multiples of this fundamental unit of energy, which he calls a quantum. And so the way that we can quantify how much energy is actually associated with that is using this equation. Now, we saw this equation on the previous slide where we did the calculations of energy using frequency. Now we have another reason for it. This tells us, okay, if I have light of a particular frequency that's being emitted, it must have that particular energy. And so that must be the energy difference between the two energy levels that the electron was going between. Now, since often we are looking at things in terms of wavelength instead of frequency, what we've done here is we've taken that speed of light equation and we've twisted it around and substituted to give us this equation. So if we really are more interested in the wavelength of light that's associated with an energy, which is normally the case because wavelengths of light are a lot easier to measure than frequencies, this is ultimately the equation that we will use, where we can put in our frequency of light, again, in meters, and it'll end up giving us an energy for that light in joules once everything kinds of cancels out. Now, before we put this completely away, I want to kind of give you a concept, a model, something to kind of grasp onto that'll help, because this idea of quantization and the differences between quanta states and continuous states can be kind of confusing. Here's a relatively simple drawing, though, a simple example. Imagine that you need to go from the top of the stairs to the bottom of the stairs. Well, there are two ways that you can go about it. There are the steps themselves, or you can take the ramp. Now, if you take the steps themselves, there's a certain amount of energy that is going to be associated with going from the first step to the second step to the third step to the bottom. While it is possible that you could skip steps, what you can't do is you can't go to any place in between. So if I want to land my shoe right here in the middle of the first and the second step, I can't do it. There's no place for me to put my shoe so that I am standing in between these two stairs. I either have to stay up high or I have to come down to the middle step. I can't go anywhere here in the middle. That's quantization. Quantization says that there is a discrete amount of energy that has to be inputted or outputted, and anything other than that cannot happen. This is different from continuous light spectrum, because if I want to stop right here on that ramp, there's nothing stopping me from doing so. And if I want to stop right here, or right here, or right here, or really anywhere on this ramp, again, there's nothing stopping me. I can put my feet on any of these positions, and the ramp will be there to support me when I do. But on the steps, I can only be in very specific places. In particular, there are 4 positions: top of the stairs, first step, second step, bottom of the stairs. I can't be anywhere other than one of those 4 positions, at least not on the staircase. So that's what quantization is all about. Quantization tells us that there are very specific energy levels that are possible, and any other energy state, at least for a given atom, is not possible. And so that's why atomic spectra look the way that they do. That's why we have those very discrete lines, whether they are bright lines or dark lines. The only difference between the bright lines and dark lines was a matter of what was happening to the energy. For the bright lines, energy was being released. So we were going down the stairs in that case. Whereas the dark lines were going the opposite direction. We're going up the stairs. In that case, the atom is absorbing energy. As it absorbs that energy at that particular frequency, it's going to show up as a dark line instead. So that's the end of this particular video. What I want you to do now, again, don't worry about going here to do it. What I want you to do now, go back into Top Hat, assignment 3-1. I need you to evaluate how you feel after watching this video. So using the stoplight question here, go ahead and just click on the area that you think best describes your level of confidence. And that is it for this particular mini lecture. So thank you for your attention here, and I will see you next time in class.